The ice here isn't just a surface layer, it's an impenetrable mass. In some regions, its thickness reaches nearly 3 miles. On the surface, there is polar night and long months without sunlight, and deep within the continent, the officially recorded lowest near-surface air temperature on Earth was measured at negative 128.5 degrees Fahrenheit. And yet, beneath all this, there is liquid water under the ice. It forms due to geothermal heat, and the friction of ice against bedrock gathers into lakes and flows through hidden channels for hundreds of miles. Beneath the eternal darkness of the ice shelves lies an entire ocean, sealed beneath an icy roof. And although the pressure here could crush a submarine, life has still found a place where it can quietly thrive. Today, we'll reveal an entire continent hidden beneath the ice. We'll explore how scientists managed to peer deep into the glaciers and discover metabolically active communities of microbes that build entire ecosystems powered by chemical energy without any sunlight. Why does Antarctica no longer seem so remote from everything? And why is studying it becoming more important than Mars? How does it affect the safety of coastal cities? And what happens when the special rules designed to prevent competition over this place from turning into military conflict and resource exploitation expire? So, to begin with, by area, it is the 5th largest continent on Earth, about 5.5 million square miles, making it nearly twice the size of Australia. The Antarctic ice sheet holds an immense volume of ice and a significant share of the world's fresh water. If it were to melt completely, it would mean a global sea level rise of around 200 feet. Climate extremes here aren't measured by cold alone. In coastal regions, katabatic winds have been recorded at gusts exceeding 152 miles per hour. While on the high plateau, months of complete darkness are possible. This makes the continent both a laboratory and a trap. Any logistical mistake here can't simply be fixed tomorrow. Antarctica's key scientific resource is the memory of the atmosphere and climate. Tiny bubbles of ancient air trapped in ice cores allow scientists to reconstruct past concentrations of CO2 and methane, while water isotopes reveal historical temperatures. The longest continuous records from Antarctic ice reach about 800,000 years, and in early 2025, the Beyond Epoca project reported recovering ice more than 1.2 million years old at the Little Dome Sea site. But there is one problem. This archive is not guaranteed to survive. Satellite observations show a long-term loss of mass from the Antarctic ice sheet and its growing contribution to sea level rise. This is one of the reasons why, in today's scientific and political reality, the continent matters more to many people than Mars. The red planet cannot flood thousands of coastal communities. But first, let's talk about life. Beneath the ice sheet, hundreds of subglacial lakes are known. Surveys indicate that more than 400 have been documented. Among them are large, stable bodies of water, as well as active lakes that periodically fill and drain. In 2025, the European Space Agency published results from an analysis of a decade of Cryosat-2 data. 85 previously unknown active lakes were identified, bringing the total number of known active lakes to 231. These lakes operate in cycles, filling and draining, causing the ice above them to rise and subside. Co-author Anna Hogg emphasized that subglacial hydrology is far more dynamic than previously thought and must continue to be monitored. The same data also revealed interconnected lake networks and new drainage pathways. And this isn't just a story about hidden rivers for the sake of mystery. It points to a missing component in ice behavior models. Water at the base can reduce friction between ice and bedrock, accelerating the flow of ice toward the ocean. But our real question is there life where there's no light? And the answer has long been yes, because metabolically active microbial communities have been confirmed in subglacial waters. Research at Lake Willans points to a diversity of bacteria and archaea that rely on reduced compounds of nitrogen, sulfur, iron, and methane as energy sources. In other words, on chemosynthesis rather than photosynthesis. Beyond that, there's another outlet of subglacial chemistry, the so-called blood falls. It's an iron-rich hypersaline brine that periodically emerges at the edge of Taylor Glacier in the McMurdo Dry Valleys. Studies have shown that even with an extremely cold glacier, an active internal brine system can exist. Radar profiling has helped map these zones within the ice sheet. Scientists have described a microbial cycle of sulfur and iron within it, a striking example of how chemistry, instead of sunlight, can become the foundation of an ecosystem. Such unique environments exist right beside the glacier in Antarctica's dry valleys. Annual precipitation can be extremely low, and conditions resemble those of a polar desert. That is precisely why anomalies like the red brine appear so alien and out of place. And even on the surface, sterility is only relative. Along the coast of East Antarctica, researchers sampled what looked like ordinary contaminated snow. Green patches formed by microscopic algae. Yet inside this snow, genetic sequencing revealed entire microbial communities. Dozens of fast-growing bacterial strains were isolated from these samples. To identify them, scientists used a method based on analysis of 16S ribosomal RNA, a molecular marker present in all bacteria. By comparing small variations in this gene, researchers can determine which microbial groups are present, even in environments where cells are extremely scarce. The results showed that many of these organisms are psychrophiles, bacteria that don't merely survive in the cold but actually require low temperatures for efficient growth. Others are psychrotolerant species, organisms capable of withstanding freezing conditions while remaining metabolically alive. These microbes are not frozen relics. Laboratory tests demonstrated enzymatic activity at temperatures close to 0 degrees Celsius. This means their cellular machinery, the proteins that drive chemical reactions, continues to function under conditions that slow down or disable most organisms. In other words, even in snow that never truly melts, biological processes are still ongoing. And this simple fact changes the role of the continent. If metabolism can persist within ice, then Antarctica is no longer just a climate archive. It becomes a natural laboratory for understanding where else life might exist. In particular, at Concordia Station, scientists monitor the microbiological background of surface snow with extreme precision. The goal is not only ecological, it's procedural. Before searching for life beyond Earth, researchers must first understand what survives here and how easily human activity can leave biological traces. Snow collected around the station is analyzed to distinguish native microorganisms from accidental contamination. This work directly informs planetary protection protocols. If a spacecraft carries microbes from Earth, even unintentionally, any future discovery of life could be compromised. That's exactly why robotic systems are being tested here. NASA's Endurance autonomous vehicle explored Antarctica's subglacial lake waters as a prototype for future missions beneath extraterrestrial ice. Ice fin descended through ice shelves into hidden cavities, environments considered close analogs to subsurface oceans on other worlds. Europa likely hides a global ocean beneath its icy crust, while Enceladus ejects jets of water vapor from fractures in its frozen shell. If life can remain metabolically active inside Antarctic ice and subglacial waters, then similar biochemical resilience elsewhere becomes a testable hypothesis. And here we face a dual challenge, reaching these environments and making sure that whatever we find there did not originate here on Earth. And the connection between this place and space doesn't end there. Antarctica is the largest meteorite collection site on Earth. Scientific literature notes that more than 60% of all meteorite finds worldwide come from this region, and the reason is practical. Dark fragments are easy to spot on the ice, and glacier flow combined with so-called blue ice areas concentrates this cosmic material and brings it to the surface. And yet even this collection is vulnerable. A recent study published in Nature Climate Change shows that as temperatures rise, meteorites begin to sink into the ice more rapidly due to surface melting, meaning the share of accessible finds could decline significantly in the coming decades. But this continent doesn't only preserve the past, it also listens carefully. Deep beneath the South Pole, frozen into the ice, lies a very special instrument. IceCube Neutrino Observatory is not a telescope in the traditional sense. It is a cubic kilometer of clear Antarctic ice equipped with 5,160 optical sensors arranged along 86 vertical strings. These detectors are embedded at depths ranging from 1,450 to 2,450 meters beneath the surface. The ice here is exceptionally transparent. Air bubbles have been compressed out over thousands of years. When a high-energy neutrino collides with an atom in the ice, it produces a faint flash of blue Cherenkov light. Sensors detect this light. Neutrinos are almost massless particles that rarely interact with matter. They pass straight through the stars, planets, and even entire galaxies. Detecting them is extraordinarily difficult, which is why a detector on the scale of a cubic kilometer is required. IceCube Neutrino Observatory has traced neutrinos back to distant astrophysical sources. In 2018, it linked a detected neutrino to the Blazer TXS 0506 plus 056, located more than 4 billion light-years away. The ice that once trapped meteorites now serves as part of an observatory watching the universe in real time. And this connection continues at the surface. Above the ice, Antarctica also observes the universe across electromagnetic wavelengths that are almost inaccessible elsewhere on Earth. The Central Plateau, especially high sites such as Dome A and Dome C, has become the focus of detailed atmospheric studies. At Dome A near Kunlun Station, long-term measurements have confirmed that winter values of precipitable water vapor often fall below 0.2 millimeters. In practical terms, this means the atmosphere contains almost no suspended moisture that would otherwise absorb infrared with terahertz radiation. Water vapor is the main limiting factor for ground-based infrared astronomy. At most mid-latitude observatories, even the very best ones, atmospheric water content can be 5 to 10 times higher. On the Antarctic plateau, entire spectral windows open up. In the terahertz range, a regime critical for studying star formation and molecular clouds, the difference becomes decisive. Some frequencies that are effectively blocked elsewhere become observable here during winter, but that's only part of the equation. During site surveys, atmospheric stability was also measured. The turbulent boundary layer, the zone of chaotic air motion that distorts images, can shrink to less than about 20 yards under calm winter conditions. Above it, the air column becomes exceptionally stable. This combination, low water vapor content, prolonged darkness, and stable stratification, creates observing windows that last not hours, but weeks. Chinese Antarctic teams deployed instruments such as SeaStar and the AST-3 telescopes to assess optical transparency and the feasibility of continuous monitoring. And these platforms were not merely exploratory. They served as technical and economic proof of concept for installing larger aperture instruments in the future. The plateau itself functions as a natural extension of the instrument. The ice preserves the clarity needed for neutrino detection. The atmosphere filters infrared wavelengths with minimal absorption, and the polar night removes solar interference for months at a time. Under such conditions, scientific presence turns into technical capability. Yet not everything here can be observed through telescopes or underwater cameras. Some structures beneath Antarctica are visible only through indirect signals, through subtle changes in gravity itself. And one of the most widely discussed such structures is the Wilkes Land Anomaly. Deep beneath East Antarctica, gravity measurements reveal a circular anomaly roughly 300 miles across. It can't be photographed, it can't be sampled directly, it can only be detected through changes in the Earth's gravitational field. This structure shows an unusual pattern, a large negative anomaly ranging from tens to more than 100 milligauss below background levels, surrounding a central positive mass concentration. This configuration matches what geophysicists call a Mascon signature. Here it's important to maintain the line between intrigue and replacing facts. The origin of the structure has not been definitely established because it's buried beneath ice and there's no direct rock samples with diagnostic impact signatures. Scientific reviews explicitly list alternative explanations, and this isn't a polite just in case, but a reflection of genuine uncertainty. The giant asteroid impact hypothesis remains one of the leading possibilities. Some studies have discussed a potential link between this structure and the Permian mass extinction, but this remains a hypothesis-level discussion. There's no connection proven without direct geological evidence from the site itself. Still, the core fact remains. Deep beneath East Antarctica lies a vast structure that we cannot drill into, cannot sample, and cannot image directly. Whether it's an impact scar, a remnant tectonic structure, or an ancient basin, its origin remains unresolved. Uncertainty on this scale is rare. And it's precisely this combination of science, potential resource deposits, and unknown future value that explains why Antarctica is governed not by ownership claims, but through international agreements. Antarctica is not divided by borders. It's governed under a treaty system, the Antarctic Treaty, signed in 1959 at the height of the Cold War. It froze territorial disputes and declared that the continent must be used exclusively for peaceful purposes. Military bases and maneuvers are prohibited, though the use of military personnel and equipment is prohibited for scientific and other peaceful activity. From the very beginning, science became the acceptable form of presence. In 1991, the Protocol on Environmental Protection to the Antarctic Treaty, often called the Madrid Protocol, strengthened this framework. It designated Antarctica as a natural reserve devoted to peace and science, and prohibited mineral resource extraction. The ban has no fixed expiration date, but there is one condition. 50 years after the protocol entered into force, any consultative party may request the convening of a conference to review its operation, and that year is 2048. However, this does not mean the continent will automatically become open to mineral extraction. Changing the regime would require consensus among the consultative parties, followed by ratification and the establishment of a new legally binding regulatory framework. Authority within the Antarctic Treaty System is procedural. Consultative parties vote. Everyone else observes. Here, status is determined not by geography, but by demonstrated scientific activity. That's why infrastructure matters. Every year-round station increases logistical independence. Every supply route expands operational reach. Every new runway reduces reliance on external coordination. In 2024, China opened the Qingling Station on the coast of the Ross Sea, its fifth Antarctic research base and its third designed for year-round operation. Officially, its primary mission is climate research and atmospheric monitoring. But within the treaty system, permanence translates into influence. The Congressional Research Service notes growing strategic interest in the region, including concerns over the expansion of China's presence and questions about the long-term stability of the governance regime under changing environmental conditions. Meanwhile, Russia continues geological research in parts of East Antarctica. And although mineral extraction is prohibited, reports of seismic surveys aimed at assessing hydrocarbon potential have drawn close attention and political reactions. The treaty remains in force, but the surrounding environment is changing. Competition is not confined to the continent itself. The Commission for the Conservation of Antarctic Marine Living Resources regulates fisheries on the basis of consensus. However, recent sessions have shown how easily proposals to establish marine protected areas or to manage krill harvesting can be blocked. Consensus is the system's strength. It's also its limitation. Today, Antarctica is still governed by law, but here law is built on participation, infrastructure, and permanence. Those who operate stations, who maintain year-round access, who build the largest logistical networks, they won't just collect data. They will shape the system itself. Physical presence may matter more than official statements within the framework of the Antarctic Treaty System.